Hey everyone, welcome back. My name is Professor Andrew Timming, and I'm very pleased to welcome you back to this lecture series corresponding to my textbook, Applied Statistics, Business and Management Research. So you will recall that in the last chapter, in chapter 5, we looked at the independent samples t-test primarily, and a bit on the paired sample t-test as well. And you'll also recall that when looking at the independent samples t-test, essentially what we're doing is we're comparing two mean scores across two groups and trying to determine whether or not those group differences, the mean score differences within our sample, are sufficiently large to generalize to a wider population. So in this lecture, we will be looking at a similar method, and this is referred to as the analysis of variance, also more commonly called the ANOVA. Probably the most commonly used statistical test among psychologists in the world. So the ANOVA, similar to the t-test, looks at group differences, but instead of looking at group differences across two groups, it looks at group differences across three or more groups. So if you haven't already listened to the lectures corresponding to Chapter 5, please do so now. They'll provide you with a nice conceptual foundation to better understand this chapter. And here we have the textbook that we're using in this lecture series. It is a textbook that I wrote. It's entitled Applied Statistics, Business and Management Research, and published by Sage. As I said, the lecture that you're currently listening to corresponds to Chapter 6. So I would advise you to read Chapter 6 before listening to this lecture. All right, let's dive right in, shall we? Okay, so what is an analysis of variance? What is an ANOVA? We'll start with the most basic question, and then we'll move on to get a little bit deeper in terms of our response to this question. So an ANOVA test is a statistical test that compares mean scores of the dependent variable across three or more categories or groups of the independent variable. So as I said before, it's similar to the t-test, except something of an extension of the t-test because we're looking at three or more categories rather than simply two categories as we would with the t-test. Similar to the t-test, ANOVA is also a parametric statistical test. So what do we mean by a parametric statistical test? This means that the test itself is predicated on the assumption that the distribution of the dependent variable is roughly normally distributed. So if your dependent variable is not normally distributed, this can introduce various difficulties in terms of our ability to accurately generalize the results from our sample to our population, to generalize the mean differences that we've encountered in our sample to the wider population. It is also, like the t-test, a bivariate test. So bivariate meaning that there are only two variables associated with it, x and y is what we call them, x corresponding to the independent variable and y corresponding to the dependent variable. And in the case of an ANOVA, the x variable has to be nominal with three or more categories, and the y variable has to be either ordinal or preferably scale level in measurement. I say preferably because scale level variables tend to be more normally distributed than ordinal level variables, but we can still use ordinal variables with this statistical test. The one-way ANOVA, so there are different types of ANOVAs. There's two-way and multiple different manifestations of this test, but the one we're looking at in this chapter is the one-way ANOVA. So the one-way ANOVA compares mean scores across three or more independent samples or groups. But another form of ANOVA is called the repeated measures ANOVA. And the repeated measures ANOVA is similar to the paired sample t-test. It compares mean scores within groups, but across time. So for example, at time 1 and time 2. Similar with the last chapter, we're going to focus primarily on the one-way ANOVA in this lecture series, and we'll cover the repeated measures ANOVA just a little bit at the end. You will recall from the previous chapter that when we carry out a t-test, an independent samples t-test, the first thing that we do is we calculate something called a t-statistic, and that t-statistic tells us something about the magnitude of the difference between the two mean scores. In the context of an ANOVA, in a one-way ANOVA, we calculate something similar, but this time it's called an F statistic. And attached to the F statistic will be a p-value. So the larger the value of F, the larger the value of the F statistic, the more likely our p-value will suggest statistical significance. And our p-value suggesting statistical significance implies that the mean differences within our sample that we've encountered probably or most likely generalize to the wider population. So we start by, when we carry out an ANOVA, we start by calculating the F statistic. And this F statistic says something about the magnitude or the difference in mean scores within our sample. This is the result of the ANOVA, the F statistic. And as the F statistic gets larger, your p-value will tend to get smaller, and a p-value that's smaller suggests a greater confidence in our ability to generalize from our sample to our population. You'll recall from previous lectures that the cutoff that we usually use to delineate statistical significance in any statistical test, inferential statistical test that is if p is less than 0.05. So if our p-value, which is derived from the F statistic, is less than 0.05, then we will conclude that the mean differences across our 3 or more groups within our sample are sufficiently large to warrant a generalization or some sort of quantum leap from the sample to the wider population. Now, the reason I taught you about the t-test before the ANOVA is that the t-test is a simpler statistical technique compared to the ANOVA, and I'll explain why that's the case now. So when you're carrying out a t-test, you're only comparing two mean scores. So the mean score corresponding to group 1 and the mean score corresponding to group 2. And the result is either significant or it's not significant. If it's not significant, then we do not generalize our result to the population, and if it is significant, then we do. Now, as I said, ANOVA follows a similar logic. It's also comparing mean scores. But the difference here is that an ANOVA test compares multiple mean scores. And this makes it difficult to understand where exactly the mean differences are. So if we have 3 groups as opposed to 2, there may be different configurations of statistical significance across those 3 groups. So when we do an ANOVA test and we calculate an F statistic, and corresponding to that F statistic is a p-value, and if our p-value is less than 0.05, then we're going to conclude that there is a significant difference in means somewhere. We don't know exactly where that difference is, but we know that there's going to be a significant difference somewhere. So just to give you an example, let's assume we have 3 groups in our independent variable. We'll call them groups A, B, and C. You run an ANOVA and you find a statistically significant result. Okay, but what does that mean? If you look more closely at the differences across the different pairs in those 3 groups, you might find, for example, no significant difference at all between A and B, but a significant difference between, for example, A and C and B and C. So it's these differences that result in the overall statistically significant ANOVA test. In order to unpack where exactly the mean differences lie, what you need to do is to carry out, subsequent to your ANOVA test, a series of what are called post hoc pairwise comparisons. So these are similar to a bunch of little t-tests that compare every possible configuration within your ANOVA. But the advantage of these post hoc pairwise comparisons, as opposed to carrying out a bunch of t-tests, is that they correct for a problem called family-wise error. So if you make a whole series of t-tests, rather than conducting one ANOVA with a series of post hoc pairwise comparisons, you can end up making mistakes in your ability to generalize because of those multiple tests. But using post hoc pairwise comparisons, a correction is built into that statistical mechanism such that the p-value cutoff is more conservative. In other words, you're less likely to make a mistake when generalizing from your sample to your population when you use post hoc pairwise comparisons. All right, let's take some time now to think about the types of research questions that we could ask as data scientists, as social scientists, and answer using a one-way analysis of variance, a one-way ANOVA test. So I've given you a few examples here of actual questions that you could ask and answer using an ANOVA. First question, are there differences in number of sick days by religion? Right, so you've got an independent variable here. This would be religion. And you've got a dependent variable here. This would be the number of sick days. And our categories in our independent variable are Catholics, Protestants, Jews, Muslims, atheists, and other religions. And essentially what we're looking at is, does the number of sick days differ across these categories? Next question, are there differences in organizational commitment by working location? So our independent variable here is working location, and I've identified three categories. So the first category is working exclusively from home. The second category is working exclusively from the office, and the third category is hybrid. And what we're trying to do here is to try and look and find out whether or not levels of organizational commitment are significantly different across these three categories. Third question, I'm not sure why anyone would want to ask this question, but I just put it in there for illustrative purposes. I don't think that you would find anything interesting or significant, although you never know. You might be surprised. But are there differences in productivity by favorite color? So you ask a group of people their favorite color, and I've got some options here: red, orange, yellow, green, blue, indigo, violet, and other color. And then we also measure their productivities, and we look with their level of productivity, and we look to see whether or not those productivity levels are different across those categories. Are there differences in productivity by relationship status? So for example, we have employees that are married, divorced, single, or widowed/widower. In this case, our independent variable is relationship status with 4 categories, and our dependent variable is some measure of workplace productivity. Are there differences in trust in management by race? So let's say if you're trying to find out whether or not people of particular races might express more or less trust towards their managers in a workplace. In this case, race would be your independent variable. We have white, black, South Asian, East Asian, mixed race, and other race. And our dependent variable would be some measure of trust in management. So think just for a moment about the types of relationships you might expect across these research questions. Okay, here are a few more research questions. We've got, are there differences in job satisfaction by sexual orientation? So we could measure our independent variable sexual orientation across, for example, 3 categories: heterosexual, homosexual, and bisexual. Obviously, there's any number of categories that we could use. I'm just giving 3 as an example. And then we could look at whether or not members of each of those groups differ by job satisfaction, some measure of job satisfaction, which is our dependent variable. Are there differences in collegiality by job type? So job type in this case would be our independent variable. And we could break this up as blue-collar workers, white-collar professionals, and managers. And then we could use some measure of collegiality as our dependent variable. Are there differences in workplace stress by subsidiary or workplace? So this would be an example of an ANOVA where the organization is the unit of analysis rather than the individual. So in this case, the subsidiary, the workplace, would be our independent variable. We've got workplace 1, workplace 2, workplace 3, etc. And then we would look for differences in workplace stress across those categories. So I think this last one might be kind of interesting to elaborate on. Are there differences in employee performance by background music? So if you're a manager and you play background music, does that differ? Does that result in differing levels of employee performance? So let's take a little bit deeper look at this question. So our question is, are there differences in employee performance by office background music? I personally would find this an interesting question to ask, and we could answer this question using an ANOVA. So what's our independent variable in this case? Our independent variable would be the type of background music played in an office setting. And our dependent variable in this case would be some measure of employee performance. So that could be an objective measure or a subjective measure. There are different ways you could do this. So how would you measure your independent variable? Well, you could simply play different categories of music, right? You could play rock and roll music, you could play classical music, you could play jazz, you could play rap. There's any number of different categories that you could employ for this particular statistical test. How would you measure your dependent variable? So maybe if this is an office where they're making sales, for example, is the objective, you could look at total sales per office, per individual. You could also, if it's an office where they're making an actual product or something like that, you could look at the number of products made, or you could also use some kind of managerial evaluation of employees. So ask the manager to rate how productive or high performing an employee has been, and then use that rating scale as the dependent variable. So how big of a sample will you need? Well, the bigger the sample, the better. You're going to certainly want a couple hundred, perhaps even a couple thousand would be ideal. What kind of result might you expect? You can speculate here. My guess is that if you were playing hard rock or metal music, you might end up with lower levels of performance compared to, for example, classical music or jazz, but I guess this is an empirical question that would probably need to be answered empirically. And lastly, how could you use this research to improve management decision making? Well, if you found that certain types of music were associated with higher levels of productivity, then you could ensure that that type of music is played in your workplace. And here's another question that we could look at more in depth using an ANOVA, for example. Are there differences in IQ by musical preference? Again, I think this would be an interesting empirical question to ask. So what is our independent variable in this case? Our independent variable would be the same as the last one, musical type or musical preference. How would you measure that independent variable? Same way, we could look at whether you prefer rock and roll, whether you prefer heavy metal, whether you prefer classical or jazz, etc. And our dependent variable would be IQ or intelligence or G. There are various ways you can describe this. And how would you measure your dependent variable? Well, there's any number of IQ tests that you could administer to individuals in order to determine their intelligence. How big a sample you need? Again, a couple hundred would be great. A couple thousand would be ideal. What kind of result might you expect? Well, similar to the last slide, you might expect that individuals who have a preference for classical music might demonstrate a higher IQ than those who like metal music or any other type. But again, this is an empirical question. Nobody knows the result of this unless someone's done this exact study before. And you would actually have to carry out the research to find out whether or not your suspicions or your hypotheses are confirmable. How would you use this research to improve management decision making? Again, you could simply look at whether or not musical preference predicts IQ, and if it does, then potentially you could factor that into an employee selection system, obviously being mindful of equalities legislation and ensuring that you're not breaking the law in doing so. So the assumptions underlying ANOVA, one-way ANOVA, are similar to the assumptions underlying the t-test. You should already be familiar with these assumptions from the previous chapter. So the first assumption is that our sample should be randomly drawn. A randomly drawn sample is one where every individual in the sampling frame or in the population has an equal chance of being selected into the sample. And the reason we prefer randomly drawn samples to non-randomly drawn samples is that the former are more likely to be representative of the population. In other words, more likely to look and behave like the population. The independent variable must be a 3-category nominal variable. This is only partially true. In theory, you could do an ANOVA with only 2 categories, but it wouldn't make any sense because if you only had 2 categories, then you would do a t-test instead. So for all practical purposes, we'll assume that when carrying out an ANOVA, there should be 3 or more categories. And these 3 or more groups must be independent of one another. So this means that, for example, membership in one group should not depend on another group. The dependent variable must be ordinal or preferably scale in measurement. I already talked about why this is the case. The reason is that the dependent variable has to be roughly normally distributed. This is a parametric statistical test, and a parametric statistical test employs the normal curve, the normal distribution, and our knowledge of the geography of that distribution in order to generalize from our sample of the population. And lastly, similar to the t-test, the variances across the groups must be roughly equal. So the spread of scores across the groups have to be more or less the same. And this is referred to as homogeneity of variance. And we test this similarly using Levene's test, as we learned about in the previous chapter. All right, so thank you very much for tuning in to this lecture, and stay tuned for the next lecture. This will be Chapter 6, Lecture 2, where we will go a little bit more in depth into the calculation of the F statistic, and we'll go through an example of how to carry out an ANOVA test. Looking forward to seeing you soon. Thanks. Bye, everyone.